All right, so we're going to start talking about wave behaviors. So the first one we're going to talk about is reflection. Everyone knows what a reflection is. It is simply because the bouncing back of a wave as it meets a boundary or a surface. So echoes, as you yell through a cave or a valley and you hear your voice echo back at you, that's because the sound waves are bouncing back off of the surfaces, the trees, the buildings. In a mirror, as you can see, your reflection is bouncing off of the mirror. Our next one is refraction. So refraction is the bending of waves as they pass from one medium to another. So as you can see, a lot of examples include objects that look distorted. So this pencil looks like it's going this way, but then in the water, in the glass, it looks like it's bent. So there's this area of refraction where the waves bend because you're changing medium. You're changing from air to water. Another example is if you try to shine a light through water, the light waves are supposed to be entering here, but because we're changing medium, air to water again, it actually gets refracted. Another real life example would be if you've ever gone fishing and you can see where your line enters the water and it looks like it's bending or broken, that's refraction. Or if you see something in the bottom of a pool and it's in the shallow end and you try to reach down and get it and you know where it is, you're reaching down exactly where you just looked, but it's not exactly there. That's also refraction. The next one is diffraction. So diffraction is the bending of waves around an edge. So refraction, going back, is just the bending of waves as it changes from one medium to another. There's no object in between. It's just that you're changing a medium, air to water, water to air. Diffraction is also the bending of waves, but it's around some edge or some obstacle. So here in this picture, this would be our obstacle. You have ocean waves entering this way, and as it hits the obstacle, the waves are bending around to go through. So as you can see, the waves at first, the original waves are horizontal lines. But then because it's having to bend around the edge or go through an obstacle, the waves end up changing to be curved. So they do get changed a little bit because they're bending to go around that obstacle. A good example of diffraction in real life would be if you're sitting in a classroom or you're sitting in your bedroom and you can hear your sibling talking in the next room over. That's the sound waves diffracting. It's bending through the doorway, bending around the corner into your bedroom. So the sound waves are diffracting as they go from your sibling's bedroom to your bedroom. Okay, now for wave interactions. So interaction just means that two or more waves are combining. So they're interacting with each other. They are in sync with each other, sort of. So there are two types of interactions. The first type is constructive interference. So when you think of construction or constructive comments, they build you up, right? If it's a constructive comment, then it's building you. If it's a construction site, they're usually building something. So hold on to construction and build. Now, destructive, you should be thinking destroy, and that's exactly what happens during this destructive interference. So we're going to look at both examples. So constructive interference is when waves combine to create bigger waves. So the waves are much bigger than they were before. So if you look in this first example where there's two people holding a rope and they both send the waves towards each other. So one's going to the right, one's going to the left. Now, in the middle, when they interact with each other, this is the interaction. This is constructive interference. So as you can see, the amplitudes got much larger, right? So you sum the amplitudes of the wave, you add them. And then, of course, with interference, the waves don't just pause there with the rope. The amplitudes continue going. So they continue as if nothing happened. Their amplitudes aren't changed. They still continue just as they were. So this first wave with this larger amplitude, it was moving to the right, and so then it continues moving to the right. See? And it's the same amplitude. Same thing for the other wave. So for the other wave, has a smaller amplitude and it's going to the left. Now here it is again after the interference, that small amplitude moving to the left. So they keep moving exactly how they were already moving. Another example is the A and B waves moving down here. So another constructive interference because you have a crest and a crest being added together. At this moment of interference, you add the amplitudes. So maybe they both had an amplitude of 1. So now their new constructive interference amplitude at this moment that they are superimposed or on top of each other, their amplitude is now 2. Then they continue moving as if nothing had happened because nothing changed, so now their original amplitudes still remain. Also, it could look like this, where the green wave is wave 1 and 2. And as you can see, the green wave is the largest amplitude wave. So it's the addition of wave 2, this small little wave here, added with wave 1, this wave here. So maybe the amplitude here was 1, maybe this is 2, and then wave 3, when you add them both together, is 3. Okay, so on the other hand, you have destructive interference, where we're going to destroy the amplitude, essentially. So when waves combine to form a smaller or no wave during that moment where they are interfering with each other. So sometimes it may completely cancel out, where you would have no amplitude, but sometimes it's just the difference between the two amplitudes. So maybe it just weakens it. So it would be weaker than the original two. So let's look at our graphic on the right-hand side for destructive interference. First, you have amplitude A and amplitude B. They look equal, right? So maybe this is amplitude of 1, this is amplitude of 1. They look the exact same. However, A is a crest and B is a trough, so they're opposite to each other. During this interference, notice you have no amplitude. This is A and B added together on this line here. So there is no amplitude. They completely canceled each other out because if you take the difference, 1 minus 1, 0. And then, of course, after the interference, you still have A with that same amplitude continuing in that same direction, going to the right. And you still have B, which is still a trough, same amplitude, and going to the left, just like before, going to the left. If you look at our picture on the left-hand side, you'll see that it's a little bit different than last time, right? So wave 1 is actually this orange line. So you'll notice that this orange line is the tallest amplitude, the greatest amplitude. Then you add in wave 2. So wave 2 is actually this blue line, and notice how it's the opposite. So whereas wave 1 had this crest, wave 2 has this trough. Then it has a crest, then it has a trough. So then when you superimpose them or they interfere with each other, what happens is you have to take the difference because you have a crest and a trough. Those are not the same thing. You can't just add them. You have to subtract. So maybe wave 2 had an amplitude, wave 1 had an amplitude of 2, because notice how wave 1 is much taller. Maybe wave 2 had an amplitude of 0.5, because it looks very small. So you would actually subtract. So 2 minus 0.5, that would give us a new amplitude of 1.5. And that is for wave 1 and wave 2. So them added both together. All right, so for this next section, I'm going to give you some examples of wave behavior and see if you can identify them for yourself. So maybe pause for a second before I release the answer. All right, here we go. All right, what wave behavior would this be? So you have a wave entering through air, then it goes through a glass prism, then it enters out of the glass prism to go back into the air. So we're changing medium. So that would be refraction because the waves are bending as it changed from different medium. All right, what about the bear walking beside the water? What type of wave behavior are you seeing here? Right, it should be reflection. The image is being reflected off the water of the bear. What about this image? You have some sort of tower that's releasing signals, and as the signals are traveling, it's hitting some sort of hill or obstacle. But it continues to travel, and it does end up reaching this house, even though there was some sort of obstacle here. Yes, this should be diffraction. All right, what about the pencil in the cup? We did talk about this example. The pencil looks bent, so it's the bending of a wave, so it is refraction. All right, how about this fun diagram? So we have light waves entering through slits. We have a single slit here, and as you can see, all these straight waves are entering. Then they change, they bend a little bit after they enter through that obstacle. Then two slits, and they change again. And here's an area of interference where two waves or more are interacting together. But we're just talking overall for this whole picture. As it bends through this obstacle, bends through this obstacle, bends through this obstacle, that would be diffraction. All right, what about this one? So here we have a laser. It enters some sort of glass marble, and it gets bent to the right, and it kind of looks like it gets bent going straight as well. So we're saying bent, so that should be refraction. All right, what about fishing? You're trying to use a spear to aim for a fish. What your eyes see is that the fish is over here, but the real position of the fish is down here. So if you don't compensate for the apparent versus real position of the fish, you probably won't catch him. And that is an example of refraction because it's bending. All right, what about this angle of reflection hitting a surface, then bouncing off? And this is a flat surface, so it is a perfect symmetry of the angle. So if this was a 30-degree angle, this would be a 30-degree angle. So this would be reflection, yes. All right, what about as these waves pass through different size gaps? So here is a smaller gap, here's a larger gap. Notice how the waves on the other side look a little bit different based on the size of the gap. But yes, as they are bending through an obstacle or around an obstacle, that would be diffraction. All right, cool picture of a duck. I'm sure this was taken at like a zoo or something. But yeah, it looks like the duck is bent. So you have half the body here, half the body here. So that would be refraction. All right, that's going to conclude this video for today. Thanks for watching. Let me know if you have any questions.